Okay, so now let's say we want to find the volume beneath this surface. And you could calculate level surfaces or stuff like that. But shapes would be a little bit more complicated than usual, but you can understand. You could do the z equals 1 surface, z equals 2, z equals 3, and so forth, and get a contour plot. You could slice it with planes, as you wish, and get an idea of the shape of this region to make sure that everything makes sense. Okay. The volume is going to be the integral of the integral. And I guess I better write the expression down. Okay. It's going to turn out to be we integrate from y equals 1 to 3, because we're integrating with respect to y. And we're integrating from x equals -2 to 2. So, again, we can think of what I just showed you. This is the area put too many words down. Let's say it's the area should have thought in advance about how I wanted to state that. It's the area within the plane of x. This would correspond to the area within the plane x equals xy. And then you're multiplying that area by your delta x. Okay? So I don't want to notate anymore, but think of this as being the area within the plane x equals xi, even though we don't have an xi here. We just have a plain old x. And we're integrating that area then with respect to x, meaning we're summing up the products of the areas with delta x's, which are volumes of these things. Okay? Okay, well, we do this integral. Okay, we do this integration, and it's very simple. Just as we do with differentiation, when we're integrating with respect to y, we treat x as a constant. So what we're going to get is integral of x squared y, and the antiderivative of x squared y with respect to y is x squared times y squared over 2. Because if we take the y partial derivative of this, we're going to get back to xy. Then over here, antiderivative of the square root of y is 1 over 2 square root of y. And I just did that wrong. I just did a derivative. It's 2/3 x times y to the 3/2. I went the wrong direction. ask me why I did that. I don't think I have an answer. Okay, that's 2/3 x times y to the 3/2. Done correctly. Now, the way I caught that error is I then tried to differentiate what I'd written down originally. So wait a minute, that's not going to be, okay? But this will. Because derivative of y to the 3/2 is 2/3 y to the 1/2, right? And we just got to assume we understand those rules. They go way back to the first month of Calculus 1. So, power function rules. Okay, so anyhow, there we have it, okay? And I'm being careless because I keep talking and not writing down everything needs to be written down. If I look to go to the next step, I don't have what I need. All this is evaluated between 1 and 3. In other words, we're just integrating this. Treating x as a constant. So that gives us the integral from -2 to 2 of I'd like to write this out a little shorter, but I don't want to risk it. So it's going to be x squared times y squared over 2. Y is equal to 3, so that's going to be 9/2. And then 2/3 xy to the 3/2, 3 to the 3/2, well, that's 3 times the square root of 3, but I'll just write out 3 to the 3/2. Then we subtract what we get when we substitute 1, which is going to be 1/2 x squared plus 2/3 x. And we integrate that with respect to x. Well, we have 9/2 x squared minus 1/2 x squared, which is 8/2 x squared, which is 4x squared. Unfortunately, this one doesn't come out quite as nicely. You got that 3 to the 3/2. But you notice, when we integrate with respect to y, of course, we get down to this step, we're going to substitute these numbers for y. So y is going to go away. And what we have here is still the area within the plane, essentially the x equals xi plane. If we put an I on x, that's the area of what we get when we slice with the plane x equals x sub I. And that's worth writing down, but I don't have room, so I'll work it in when I'm done here. Okay, well now, this equals then simply four thirds x cubed plus three halves minus 1. Okay, in other words, antiderivative of x cubed is x squared is x cubed over 3. Antiderivative of x is x squared over 2. The 2 divides the 2 and all that. And if I wrote it down wrong, fix it. But anyhow, this is evaluated from -2 to 2. Now conveniently, this term, which is just a multiple of x squared, has the same value at -2 as it does at 2. It goes away. Okay? Gives us 0. When we subtract what we get here from what we get here, since the two are equal, we get 0. Leaving us just this. And that's 4/3 times 8 minus 4/3 times -8, which is 2 times 4/3 times 8. Okay? Which is 8 squared over 3, 64 over 3. Okay? Again, when x equals 2, we get 8 here, so it's 32 over 3. When x is -2, it's -32 over 3, so we subtract -32 from 32, we get 64 over 3. Now, I don't know if I did that right. You know, there's a little bit of arithmetic there, and I'm trying to talk and form these pictures. But one thing I want to do, and then we're going to just check to see if this interval makes sense in terms of the average value times the area of the base. What I want to say is that this expression here this, which is just this expression, okay, at xi, is the area of the slice corresponding to the plane x equals xi. So if I draw this thing here, C here, D here, talking about this slice. Just to refer back to these pictures so we understand where this comes from. Well, let's see what to do with these boards without crippling myself. That's fine, but when I hold it out from my body, I knew that anyway. Okay, so now we've concluded, or at least we're proposing a solution to the committee. He's going to try to shoot it full of holes if it doesn't make sense and embarrass the heck out of us and maybe get us a demotion. Okay, so, you know, if we're engineers, we make sure everything is right. If we're mathematicians, well, if we're wrong, we just fix it. If you're engineers and you build it and it falls down, you're in big trouble. Okay. Here's our region of the XY plane. X goes from -2 to 2, and Y goes from 1 to 3. not drawing it particularly to scale. Yeah, 1, 2, 3 should be a little higher, but okay, we get the idea. Call the region R. And we haven't sketched the 3 dimensions, but Z's out this way. Okay, well, if X is -2 and Y is 1, we can plug that in. X is -2, Y is 1, right? So we have 4 times 1 plus -1 times 1, right? And that's going to be 3. Okay, Z equals 3 here. And this is, of course, the point -2, 1. Oh, wait a minute, it's 2. Got that 1 in my head. Okay, things aren't locking in like they should. Okay. If X is -2 and Z is 3, and Y is 3, then we get 9 times 3. Okay, plus -3 times the square root of 3. Well, that's 27 minus 3 square root of 3. Okay. 3 square root of 3 is about 5, so it's maybe about 22. Now my estimate here isn't looking great because the area of this rectangle is 8, right? Could be something wrong with my integration. But let's continue. I really was trying to do the integration correctly, but so be it. Okay, if X is 2 and Y is 1, then we get 4 here and 2 here, we get 6. Z is 6. Over here, Z is what? Well, Y is going to be 3 now. So we're going to have 4 times 3, which is 12, plus 2 times the square root of 3, which is not 3, Z is about 15, approximately. My Z values are all pretty high. The average value is the integral divided by the area of the base. Just analogous to the average value function of 2 variables, which is equal to the integral divided by the length of the interval. Well, the average value is at 8/3, and that's not consistent with what we get when we evaluate the Z's. Another thing is, x squared y is always going to be positive. The only way we get a negative is with the x times the square root of y, and these numbers are always going to be less than these numbers. Just think about it. So I must have really done something stupid with my integral. Either that or this whole theory is totally incorrect, and we've based much of Western civilization on something that I've just disproven. Okay? I'm going to keep quiet about that. We're having enough problems right now. So, I'm not sure how this reconciles. I'm going to have to think about it. But there's nothing wrong with this that I can see right off the top of my head. And certainly nothing wrong with this, except that maybe my arithmetic is a little screwed up in places. Okay? But our typical values of this function appear to be way too big. Now, as we get in close to the origin, x gets small, or to the y-axis, x gets small because x gets small, so these terms become small. When I said this is always less than this, yeah, if x is bigger than 1, it is, but it won't always necessarily be true if x is very small, because when x gets very small, x is going to be bigger than x squared, right? So we could get some negative values, but they're not going to be that big. And we could explore a little further. On the y-axis, of course, z equals 0 everywhere, because we have multiples of y. Z equals 0 everywhere on the y-axis. And of course we can do y slices and do evaluation. We're out of time. If x equals 1, then we get y plus the square root of y, which is going to be 2 here. And about 5 here. Okay, over on this side, well, I'm not going to go there. I keep getting values that are bigger than 8/3, which is not even as big as 3, except very close to the y-axis. And something isn't working right.